All right, welcome back to our flipped chemistry classroom. And today we are going through an introduction to balancing chemical equations. We're going to talk about what it means for an equation to be balanced or unbalanced. And we're going to learn the process that you're going to go through to balance a chemical equation. So we're going to start with a few examples that show this process that you'll go through. We're going to look at it at a molecular level. We're going to look at it mathematically, and hopefully this will help you as you work through these kinds of problems. So we're going to start first with this equation. Hydrogen and chlorine react to form hydrofluoric acid. So anytime we have an equation like this is called a word equation because it's written in words. We're going to substitute in chemical formulas. So our chemical formula for hydrogen is just H2. We remember that hydrogen is one of our diatomic molecules, so we always have to put that little subscript 2 there. And we're going to write the and as a plus symbol. And chlorine, again, is one of our diatomic molecules, so it needs a subscript 2 as well. And they react to form, so we're going to put our yields arrow, hydrochloric acid. So we see this hydro and this ic, and we remember from our nomenclature that hydroic acids are binary acids, meaning they're just hydrogen and that element. And we know that chlorine is a -1, hydrogen is a +1, so it's just HCl. So the last thing we need to do to write this equation correctly, although unbalanced, is to go back in and put the states of matter. So we're going to say hydrogen, we know, is a gas at room temperature, as well as chlorine. So we're going to put a little subscript G in parentheses here. And hydrochloric acid, when it forms through this reaction, is actually also going to form as a gas. If there are ones that I don't expect you to know, that information will be given to you in the word equation. Okay, so we're going to take a look at what this would look like on the molecular level. So what does H2 mean? It means that there are 2 atoms of hydrogen and they are covalently bonded together. And the Cl2 means we have 2 atoms of chlorine also covalently bonded together. And then the HCl means that we have a hydrogen covalently bonded to a chlorine. And so on a molecular level or a visual level, this is what this looks like. So we have hydrogen plus chlorine yields hydrochloric acid. Now, let's take a look and see if this is balanced. And why does it need to be balanced? So a balanced chemical equation is one where we have the same number of atoms of each molecule, of each atom, on each side. And so if we look at this one, we have 2 hydrogens here, but only 1 on the product side. And we have 2 chlorines here, but only 1 on the product side. And why is this a problem? Well, our law of conservation of matter tells us that atoms can't be created or destroyed. So if I had 2 hydrogen atoms on the reactant side, I need to have 2 on the product side. And if I have 2 chlorine atoms on the reactant side, I need to have 2 on the product side. So how can we solve this problem? Well, for this one, it's pretty simple. We're just going to put another hydrochloric acid molecule on this side. Now we have 2 hydrogens here and 2 here, 2 chlorines here, and 2 chlorines here. And now we have a balanced chemical equation. So how do we represent that in our equation? Well, if I have 2 of this molecule, I put a coefficient of 2 in front of the molecule's formula. So that coefficient 2 tells me that I have 2 of this whole thing. That means I have 2 hydrogens and 2 chlorines, but they're 2 separate molecules. So remember, balanced chemical equation has to be balanced because atoms can't be created or destroyed. And a balanced chemical equation is one that has the same number of atoms of each element on both the reactant and the product side. An unbalanced chemical equation or a skeleton equation does not have the same number necessarily on both sides. Okay, so there's our first example. Let's take a look at another example. Let's get rid of these guys. And let's take a look at another reaction. So now we have hydrogen and oxygen reacting to form water. So we're going to go through the same process. We're going to write the formula for hydrogen, which is H2, again, diatomic molecule. We know it's a gas. And we're going to write as a plus sign oxygen. So O, also a diatomic molecule. So we need a 2. And that one is a gas. React to form water. Now we know that the formula for water is H2O. And so we're going to look at this visually again. So we have our hydrogen molecule and our oxygen molecule. And on the product side, we have our water molecules. So hydrogen plus oxygen yields water. So are you starting to see a problem here? Well, I have 2 hydrogens and 2 hydrogens, so that's good. But I have 2 oxygens on the reactant side and only 1 oxygen on the product side. So that's not going to work. Now, the way we're going to solve that problem is by adding another whole water molecule. So now we have another water molecule. So now I have my 2 oxygens on the product side and 2 oxygens on the reactant side. But now I have 4 hydrogens on the product side and only 2 on the reactant side. So I'm going to solve that problem by adding another hydrogen molecule on the reactant side. So now we're going to go back and we're going to use those coefficients. We're going to put a 2 in front of water and a 2 in front of hydrogen. So we've solved our problem. We have 4 hydrogens, 2 oxygens, 2 oxygens. Sometimes you might be tempted to say, well, I have an easier way to solve this. I can just put a little subscript 2 right here. Then I have 2 hydrogens and 2 oxygens, 2 hydrogens and 2 oxygens. Problem solved. Why can't we do that? Well, my reaction says hydrogen and oxygen react to form water. What we've written here is hydrogen and oxygen react to form hydrogen peroxide. That's a whole different compound, and we've totally changed the meaning of the equation. We cannot do that. So this is a big fat no-no. We have to write H2 plus O2 yields H2O. And we are going to balance that by putting coefficients. We never change the subscripts to balance the equation. The only time we can change subscripts is to write compounds correctly. Once the compounds are written correctly, we have to stop and use coefficients to balance our equations. Okay. One last practice problem. We're going to have nitrogen and hydrogen reacting to form ammonia. So nitrogen, again, is one of our diatomic molecules. So we're going to write N2. This one also is a gas at room temperature. And hydrogen, so H2, still a gas at room temperature, react to form ammonia, which is NH3 and is also a gas at room temperature. So we could do the visual representation, but I don't see you guys wanting to draw pictures on your quizzes and tests. So let's talk about a way that we can do this more mathematically and less from the visual representation. So I'm going to make a T chart. These are my reactants, and these are my products. And in my T chart, I'm going to say how many nitrogens and how many hydrogens. So on the reactant side, I have 2 nitrogens and I have 2 hydrogens. On the product side, I have 1 nitrogen and 3 hydrogens. So now, just like before when we were looking at the visual representation, we want to think about what can I multiply this by to make the numbers the same on both sides. So we're going to tackle this one element at a time. And I'm going to start with the nitrogen because I have 2 here and only 1 here. So that makes it easy. If I put a 2 in front of the ammonia, that means that I'll now have 2 nitrogens, but that 2 applies to the whole compound. So I also have 3 times 2 or 6 hydrogens. So I've solved the problem of the nitrogens, but I've created a problem with hydrogen. So now what can I multiply the hydrogen by so that I would have 6 hydrogens? Well, since I already have 2, I'm going to multiply it by 3, and that will give me 6. And now I can see that I have 2 nitrogens on the reactant and the product side, 6 hydrogens on the reactant and the product side. And if we just want to confirm for ourselves with the visual representations, we have nitrogen, we have 3 hydrogens, and then we have 2 ammonia. So 1, 2 ammonias, and you can see maybe that we now have, oops, there we go, 6 hydrogens and 2 nitrogens on each side. Okay, the best way to master this is to do lots and lots of practice. So we're going to work on these in class, but I have one for you to practice on your own. And that one is solid sodium reacts with chlorine gas to form solid sodium chloride. As always, please let me know if you have any questions, and I look forward to seeing you in class.